This video is presented to you by Physics for Students.
Okay, so in this video we are going to learn about discrete and indiscrete topology. But before we go ahead and start with this topic, I would like to give the viewers a quick recap on what we have learned. Before even giving a recap, I would like to share very good news with all my dear students, friends, seniors and the subscribers of my channel, is that Physics for Students is coming up very quickly with a brand new website which is called physicsforstudents.com. Yes, I would like to repeat, it is physicsforstudents.com. This is a website where you will get many other scientific things, just not the videos that I make. It will have articles, it will have podcasts, it will have a special topic which is dedicated to the famous Austrian mathematician and logician Kurt Gödel. Yes, you can also send your articles where we can publish this article in our website physicsforstudents.com. Even it will have a special section for podcast. If you think that you can make a podcast on your voice on a particular scientific topic, it can be technical, non-technical, it can be biographies, you are welcome. You can send your podcast, you can send your articles or writings, and we will be happy after reviewing and publishing it on physicsforstudents.com. So this is a small good news which I am very happy to share with you all, and it will be launching soon, and I will post it in Facebook and other social media. This is a website which will contain various other articles and a special section called Students Corner, where you can learn more about different topics of science on general mechanics, on topology, on general theory of relativity, on Maxwell's equations, on linear algebra and many other topics. Not only you can learn, even if you think you can contribute to this website. So this is a small news which I just wanted to share with you. Okay, so far so good. So let us see what are the things that we have done earlier in this part of topology. I would like to give you a quick recap on this. So we have learned what is a topology. We have seen a brief history on how topology evolved from Euclidean space and generalized into a topological space. We have also learned about open and closed sets. We have seen certain proofs in topology, and we have learned through illustrations and small examples of what is called a homeomorphism. So the viewers who are watching this video for the first time, I would request that please go and check my playlist in the topology playlist in the video section, where you can find all those things which I am right now displaying on your screen. Right. So once we have done a recap and we already know these topics, let us go ahead and start today's topic, which is called discrete and indiscrete topology. So what are the topics that we are going to cover? We are going to cover what is a discrete topology, indiscrete topology, coarser topology, finer topology, and definitions and proofs. So you see, in my earlier videos I generally used to make the table of contents in general text, but why I have made it in a circle, just to give you an understanding, all these topics are related to each other. That means discrete topology is related to indiscrete, which in return is related to coarser topology, again which is related to finer topology, and finally all this culminates to some definitions and mathematical proofs. So that is why I have given this display picture on a circle with arrows in order to make you understand that they are all related to each other. Right. So before we go ahead and understand what is a discrete and indiscrete topology, first we need to understand that why it is called so. Obviously it is a general question that why it is called discrete, and the curiosity arises, has it got something to do with discrete mathematics, or has it something to do with the way we understand discrete? So we can consider a set to be a discrete collection of objects, right? So objects which are separate, distinct and countable, right? So things which are separate, distinct and countable. So discrete topology is also called the finest topology. Why it is called finest? Because you cannot further subdivide it into subparts, right? That is why it is called the finest topology. Now in this regards, two terms which will come into the picture is called a finer topology and a coarser topology, which we are going to take care later. But yes, these two are also important, finer and coarser topology. So what you can see right now on the screen is that you can think of sets something like this. Again, for the viewers, I would just like to take a note is that this is an intuitive understanding of what is a discrete topology. We are right now not going into the mathematical part. Okay, so first we give you a intuitive understanding of these two things, discrete and indiscrete, then we go into the mathematical part. I think that becomes easier. So you see these are small dots which are there on the left hand side of your screen. These are indivisible. Indivisible means that which cannot be further divided, and that is why we call it finer. Finer in the sense that it cannot be further subdivided. So you can think something like this on your screen on the right hand side in blue, which is a kind of an atomic structure of Bohr, which I have given. So because general notion tells that atoms cannot be divided, so it is indivisible, something like atoms. So this is a kind of a nice analogy that you can think of discrete topology as atoms which cannot be further subdivided. So it looks like each indivisible atoms which cannot be further subdivided, and each one appears like a singleton set, right? So you see on the bottom of your screen I have given an arbitrary value x which is discrete and distinguishable, right? Each and every function forms a discrete space, right? From discrete topology we get a discrete space. So we can say that each element has its own country, own island, and that makes it discrete. So each of them has its own place, and that is why it is discrete. So we can always think of topologies as obscure or blurring together those underlying points of the set. Topologies deal with nearness, which we have seen earlier, relations, nearness relations, or points in the open set which are in the vicinity of one another. So if there are 2 points that never appear alone in one open set, those points I would say are topologically indistinguishable. So here are few important points. So discrete topology is the finest topology which cannot be further subdivided. It obscures that nothing about the underlying set. It is clearly highlighted and distinguishable, and it can be termed in terms of singleton set, which I have shown. So this is a kind of a, I would say, a very basic and an intuitive approach on what is actually a discrete topology. So here it is something which we call any set with the discrete topology is metrizable by defining. Now this is not a right English, you know, metrizable is not a right English, but I've just given that means which can be metered or which can be measured. So if I take something like this, dx of y equals to 1 for any x and y belonging to x with x not equals to y and this equals to 0, then we can tell the discrete topology is metrizable. Why? Because x is a discrete space. Every singleton x is an open set. Every subset of x containing in x is a neighborhood of x. So this is a kind of a definition that its discrete topology is metrizable. That means it can be measured. Now along with this concept of discrete topology, another concept that emerges is called a discrete space. Okay, now this is again another example of discrete space. As you can see in this figure, what do you find? This is a space, okay, that purple one, which has certain points. Those black dots, okay, circles. So discrete space is a particular example, or you can say rather a simple example of a topological space or similar structure on which the points are isolated from each other. Right, you know, that is the sense. So you see these points are isolated each other, those black dots, and I have given those red arrows in order to make an understanding that how one is isolated from each other. So the concept of isolation and discontinuity is there. So every subset here is open in the discrete topology. right? So that in particular every singleton subset is an open set in the discrete topology. So we can call this a space equipped with discrete topology is called a discrete space, right? Further, we can tell this. So points are isolated, discontinuous sequence, and it is the finite topology. Earlier I have told you that discrete topology is the finest topology, so I have mentioned it again, finest topology. Now the underlying uniformity on a discrete metric space, I am calling it metric because it is measurable. So the underlying uniformity on a discrete metric space is the discrete uniformity, and the underlying topology on a discrete uniform space is the discrete topology, which is more or less clear by this figure. So from discrete metric space we are going to discrete uniformity, and the underlying topology of discrete uniform space is the discrete topology. So this is something which we can give you an kind of an intuitive understanding on discrete topology and discrete space. Now another important feature, or rather I would say property of a discrete space, is this one. Each and every function from a discrete space is automatically continuous. That each and every function from a discrete space is automatically continuous. So if for example T is a topological space, there is always a natural bijective correspondence between this, right, and this. If I take it in this way, G is a discrete of X which leads to T. So it is something you can imagine like this, right? So you see one part is X, one is discrete X. So for every function on X we can find a continuous function on discrete X, right? So you can see the bottom arrow, from X it is leading to discrete X, right? And a given function on discrete X we can uniquely recover a function of X. So that is why I use the term that if T is in any topological space, there is natural bijective correspondence between those two, which is on the left hand side. Bijective because because X we can find a continuous function on discrete X, and given a function on discrete X we can uniquely recover the function on X. So it is discretized into individual points, right, and counting the points in discrete topology. So the discrete topology best represents the structure of the set X, which is the capital X, which we say is discretized, okay, which is discretized into individual points and counting the points in discrete topology. So counting the points in discrete topology, right? So this is something which gives you a kind of a further understanding. Now we come to indiscrete topology. So we are done with discrete topology. I think you have got a fairly basic intuitive understanding of discrete topology. Now if I talk technically, right, the collection of non-empty sets and the set X itself is always on topology on X, right? This is called indiscrete topology on X. In other words, I can tell xt, which you can see, one is the t phi comma x, and this one x comma t. This is an indiscrete space, right? So for any non-empty set X, the collection as which is shown in the screen is an indiscrete topology on X, and this one is called the indiscrete space, which you can see on the left hand side. Now this indiscrete topology has got various terms. It is also called a trivial topology, it is called anti-discrete topology, and it is called co-discrete topology. Okay, so you see here on the right at the middle of your screen. So what I have done is that those red boxes which I have shown in the discrete topology, I have taken these things together. Right, I have taken these things together, and you can see what I'm trying to mean is that it cannot be distinguished, so that this one forms something like this. So from point left hand side the red dot going to the right hand side red dot, this line, this black line, the curved line, you cannot really distinguish between those two lines. So what it leads to, it agglomerates the points of the sets together. That means conglomerates or agglomerates, it is the same. It takes all those things together, and if two points that never appear alone in an open set, those points are topologically indistinguishable. So I can call with this figure. So it is a kind of a lumped up concept. You get it? Like, I mean to say, all these points are lumped up in one space, so that points cannot be separated. It is lumped up in one single identity or something together. So this is basically again a kind of an intuitive visual understanding in order to make you understand about indiscrete topology. Okay, now what we come is that finer and coarser topology. These are all related to what we have learned. Now this figure, although these are small grains, it is giving you a basic idea of what is a finer and a coarser topology. So if I take T1 and T2 as the two topologies, you can see it in the figure that the size of the, it gives you a kind of a basic understanding that the left hand side grains are much more finer than the right hand side grain. Right. So it is more or less, a kind of an understanding, visual understanding. So it is the size of the open sets in the same sense. We think that one is a finer grind of flour than the other, and it has been grinded to a further smaller size. So this is what is called finer and coarser topology. So here in the finer topology, it cuts the space more finer and it does not cut it. So this is the basic difference. Okay, let us go to the technical definition. If T1 and T2 are topologies defined in the empty set X such that this one, that is each member of T1 is also in T2, then T1 is said to be coarser than T2 and T2 is said to be finer than T1. But there is a condition that at the bottom of the screen, you can read it. It is quite clear. If every subset on X which is open for T1 is also open for T2. Or equivalently, if every neighborhood of a point in X with respect to T1 is also a neighborhood of that same point in the topology of T1. So this is a kind of a formal proper definition of what is called a finer topology. So you can find it from here. Okay, this is an important point which I would like to make. A finer topology always has all the open sets of the coarser topology and possibly more. So it will have all the open sets of coarser topology and possibly more. The final intuition is that in some meaningful sense divide the underlying set in a more fine-grained fashion. So fine-grained fashion is the one which I showed right at the beginning, that it is chopped or cut more evenly. So now let us see that how we can define finer topology using symbol. So if S be a set and T1 and T2 two topologies on S, we say in this way: T1 is finer than T2 if and only if this one, and T1 is finer than T2 if and only if the identity mapping of ST1 and ST2 is continuous, which all these things can be written in this way. Right. So you can take a note, you can take a screenshot, or you can pause the video right at this moment and just take a note of how using symbol we can write what is a finer topology. Coarser topology, quite simple. Let S be a set. We are using the same T1 and T2 be topologies on S, and let T1 this one T2. Then T1 is coarser than T2, and we can write it in this way. So again, a request that if the viewers want to take a note on how you can write these things on symbols, you can do that, and this is how it is. Okay, so far so good. Now we observe that if T in the okay, so we are coming to discrete and indiscrete topology. So we are coming to this as a definition and proof. So we need to take hold of what is the definition and the proof, right? Okay, so first we will go for discrete topology, a technical definition. So let's see what it is. So it's simple. Okay, one more thing what I wanted to make the viewers make sure before I go ahead with this is that if you have not looked into what is a topology or what is the definition of a topological space, I would request all of you to please go there and into the first video of my playlist, which you see that topology and topological space, go through that, because I would be using now all those definitions in this particular video so that we can interlink and understand. So please go ahead and learn the first video on the topological space and definitions. So if X be a non-empty set, this, then T is called a discrete topology on the set X. The topological space X comma T is called a discrete space. Same thing I have used in topology and topological space. Now, this T, right, which I have underlined in maroon, and it satisfied all these three things, right? So D is only called a topological discrete topology if satisfied these three things, which I'm not iterating again. This is there in my video of topology and topological space. It is simple, just go through and read it. Number one, X and the empty set phi belongs to T. Number two, union of any finite or infinite number of sets in T belongs to T, and the intersection of any two sets belongs to 2. This is the first definition, and then why it is called the pair XT is called the topological space. Nice and fine. Another thing is that this one X, as you can note right here, right, it is a non-empty space and it is a discrete space, right? So look into the first definition really before we go ahead and understand. And this one, I'm sorry, this one is what is the basic definition of discrete topology. So two things you need to take a note. First thing is that X, T, how it satisfied these 3 points and definitions, and X is any non-empty set and it can have infinite discrete spaces. Now if I come to the indiscrete topology definition, again I would say this one, X phi, then T is called the discrete topology, is called indiscrete space. Same thing here also, T satisfies definition 1, which I have shown in, and X is a non-empty set which can lead to infinite amount of discrete spaces. Now before we go ahead in the next part of the video, I would like to make a note to the viewers. Those who have not seen my earlier video, just pause here and take a note of this definition 1. I mean to say Roman 1, Roman 2 and Roman 3. These three things we are going to use in order to move ahead in terms of definitions and other things. So just this is the definition of discrete and indiscrete topologies satisfying this definition. Okay. Now once we go ahead in proving, so let us assume, demonstrate it with an example. Suppose X equals to A, this one T is in topology, right, and this one, right. So how we can prove that T is a discrete topology? We have seen the intuitive understanding, we have seen the visual understanding. Now mathematically how we can prove that T is a discrete topology. So T is the discrete topology, that is T contains all subsets of X. So first of all, if it contains all subsets of X, then first let us write down what are the subsets of X, right? So we see that 2 to the power 3 2 cube, there will be 8 subsets. So what are those? So we get S1 as phi, S2, and we get S3, S4, S5, X6, S7, S8, which is ABC, which obviously includes X, which is the set, right? So now you see there what we have done. Step 1 is that we have written down all the subsets, that is the 8 subsets, right? Now from the previous definition which I told you to take a note, the first part, this one, X and the MC set phi belongs to T, this is from the first part of the definition of first definition, right? So which means this, T is a topology as per definition, right? So obviously X and phi are in T, so S1 is includes T and S8 includes T, right? So this part is done. So we have got S1 and S8. Now this comes from the first definition. So I told you the first definition is very important. All these sub 1, 2 and 3 parts of the first definition. Now we are given this, right? We all know this. A includes this, B, C, all these things, and S2, S3 and S4, right? So we need to show what? We need to show this, right? S5, S6, S7, so on, right? And if you go back earlier, we have shown S1 and S3 already done, right? So yeah, so S5 equals to this union, which we already know, and from A and B are in topology T, right, which we have shown in definition, sub definition 2 of definition 1. So from here we get this, right? So from here S5 we get this. So we underline this, and from this particular definition we go to S6, which is again in union, we get into this and we get underline this. So we got the S6 and we get S7 from here and we underline this, right? So it's pretty simple. So what we are doing is that we are using the definition, the sub definitions part, and we are trying to prove this one. So what we get from here, Now this part is proved, right? So we have got, let us go back to this. So we have got this one, S5, S6, S7. But I would like to make you a small note. Now we have shown that A, B and C are in topology T, and X, A, B, C, then T is a discrete topology. Everything is fine. But a question arises, also an obvious question arises. Now what is this question? That if X and T is any topological space such that T contains every singleton set, question is that is T the discrete topology? Right, is T the discrete topology? Obviously the answer is yes. But how do we prove that? So here it is. So if Xt is any topological space such that this one and the singleton set X is in T, then T is the discrete topology. Now it seems somehow, this definition, it seems somehow it is similar to the proof that we did just now, earlier. Right, but we have to remember one thing. We have to remember here X is an infinite set, right? And every subset of X is a union of singleton subsets are in T, right? Now because X here is, and also every subset of X is in T. So remember, because X here is infinite, we cannot just note what we did, 2 to the power 3, 2 cube equals to 8, and we write down all the subsets. It cannot be done. Right. So if we look back to the earlier example, we find out that every subset of X is a union, and we know that all the singleton subsets are in T, but we cannot do that, right? Because this is infinite. So how do we do that? Let's see. So we start the proof with this. Every set is the union of all singleton subsets. So if S be any subset of X, then we can use this, right? This is quite clear. Now as per the second part of the definition of definition 1, which I told you to make a note, this equation, it implies each X is in T, right? Definition of 1. Definition 1, the part 2, each X is in T. So this implies that S is includes T, right? And from here we can get that T is the discrete topology. So this equation, as S is an arbitrary subset of T, we can take a note on this, that T is the discrete topology. Obviously, it is an arbitrary set of T. Now just note one thing before we conclude this. Now this holds actually, this part holds actually true even with this. And this is what we called empty union, and set phi is the result. Right. So this also holds true even for the empty union, and that is why we call it as empty union, and the set phi is the result. So this is a kind of a nice understanding of the of what is called a discrete and indiscrete topology. So let us look into the quick summary. We have learned discrete topology. We have understood what is an indiscrete topology. We have learned discrete space, which is related to this. Also indiscrete space. We have also seen how these things are related to finer and coarser topology, how by definition, intuitive examples and visual demonstration we can learn, and what are the definitions and examples, and we have proved through definition and example what is a discrete and what is an indiscrete topology. So that concludes today's video. I hope you like this. I would be waiting for your comments, anything that you would like to tell. I would be coming up more on the videos on topology, but I'm a little bit busy with my new website, which is also open for you, for your contribution, for your comments, for your news and articles, and you can contribute immensely so that this website grows. Thank you very much for watching this video. Stay safe, stay happy, and have a nice weekend ahead. Bye.